Welcome back. This is part 3. I'm just going to pick up right with graphing again. All right, so transformations with the log functions. The nice thing is it's no different than with the exponential functions, really. The only thing that's different is we have vertical asymptotes with the log function instead of a horizontal asymptote. And so that's the only real difference, not the translating part. So vertical shifts, most the same as all other functions. The log is no different. You add or subtract from the whole function, it moves it up and down. It can be at the end or the beginning. So for instance, I have written up there in red and in blue, the red graph there is y equals log base x plus 3. Excuse me, y equals log x plus 3. And it doesn't matter whether it was the 3 was in front or the 3 was in the back. So y equals log x plus 3, y equals 3 plus log of x. It's the same thing. So the blue graph is our base graph, y equals log x. Our base is 10. Right? So of course, like all log functions, we're going to have the point, oops, come on graph. There we go. We're going to have the point 1, 0. Right? I should say all log functions that haven't been translated. We're going to have the point 1, 0. But it's going to take a little while for our graph to get up to 1 on the y. We're going to have to go all the way to 10. So maybe some place around there. We'll have the point 10, 1. Because if you raise 10 to the first power, you'll get 10, and 10's our base. So this is the exponent. So 10 to the first, because 10's our base, there's nothing written, gives us 10. So it takes a while for this graph to grow. But it grows real fast on the x, just real slow on the y. If we subtract from this function, we're going to move the graph down. So we haven't changed our asymptote at all. It's still at x equals 0, because we're just moving it up and down. So just like the other functions, you add, if it's positive, it'll move it up. If it's negative, it moves it down. Horizontal shifts are what's going to change our vertical asymptote. We'll know it's a horizontal shift because it has to be inside the parentheses. Okay? Has to be hooked to the x value, so it's going to be inside the parentheses. If it's not inside parentheses, then it is not added to the x, it's added to the whole function. So like for instance over here, where we have log x plus 3, or 3 plus log of x, that's added to the whole function, it's not added to x. Here the value is being added to x. So y equals log of x, the same graph, is the blue graph. If we have y equals log x plus 2. Now we've shifted our whole function 2 units to the left. You add to x, it moves it left, just like every other function. Okay? So add to left, moves it left. Subtract from x, moves it right. And the vertical asymptote changes as well. Okay? So now for y equals log x plus 2, our vertical asymptote's at -2. For log y equals log x minus 4, our vertical asymptote is at +4 because we've shifted it 4 to the right. Okay. Reflections occur because we have a negative on the in front of the log or on the x. Okay. I'll go over this briefly. I don't think it's on the benchmark, but it is something you'll need to learn. So if we have it, if the negative is in front of the whole thing, we're going to reflect our graph about the x-axis. So it's going to make the values negative, and it's going to make them the opposite. And we'll take a look more about why that occurs afterwards. And if we have the negative in front of the x, it's going to reflect it about the y-axis. Okay, so now our domain is going to change. It's going to be all the negative numbers, because we have a negative number in there. Because the negatives are already there, we can only plug in negative numbers, right? Because we can only take the log of a positive number. So if I get a negative there, I can now only plug in negative numbers. And then this one we'll talk about in class, vertical stretching and shrinking. All right, for now, if we'll just tell you something just real basic, and then we'll go over it in more detail later. But if we have a value in front of log and it's greater than 1, it's going to vertically stretch our graph. If it's between 0 and 1, it's going to vertically shrink our graph. Just think about multiplying by 5 is going to make something 5 times larger. And if you multiply by 1/5, it's going to grow 5 times slower. Okay. Oops, page is in there. Oh no, sorry. 5's in a different spot. Horizontal stretching. So this one is a little trickier to understand from the graph and see the effects from the graph. When we graph using transformations, I think you'll understand better how this really affects our graph. But now we're horizontally stretching and shrinking our graph. And you might think that having the number greater than 1 is going to stretch our graph. It's actually shrinking our graph. But it's shrinking it horizontally. It's going to grow more slowly along the x because the y is increasing a little faster. So I'm not going to go into too much detail on this. This is a little bit more advanced concept. We'll do this in class, and once we get graphing and with transformations, then I'll go over this more. So just suffice it to say that we're going to horizontally shrink the graph if the value in front of x in the parentheses there is greater than 1, and we're going to stretch the graph if it's between 0 and 1. And of course, our domain logarithmic function reverses the domain and range of the exponential. So your domain is going to be all positive real numbers unless we have a horizontal shift or a reflection. Okay? So normally, oops, my number's a little off here. Normally, our range, our domain is going to be 0 to infinity. But if we shift it to the left by 2, our domain is going to be -2 to infinity. If we shift it to the right by 4, our domain will be 4 to infinity. But our range is all real numbers. Okay, so it's those horizontal shifts affect the domain and the vertical asymptote. Okay. So and we can have both transformations in one, a horizontal and a vertical. So here's one. So the base graph there is, and it even shows you the base by putting the 10 in there. But the base graph there is y equals log 10 to the x. Our transformation is y equals log base 10 x minus 1 plus 2. So to graph this function here, we would graph the base function, which is y equals log 10 of x, and then shift it. So we would take our points, so for instance, the point 1, 0 there, and our graph would shift 1 to the right because we've got x minus 1, so that's going to shift it to the right. And then because we've added 2 to the whole function, the graph is going to move up 2. This will change our vertical asymptote. So now our vertical asymptote is going to be here. Probably should have written in blue since everything else is blue, but at x equals 1. Okay? And of course our domain would change as well. Okay, so we can have more than one transformation. All right, so which function is best represented by this graph? This is a log graph. Okay? It's got that characteristic log shape where it's growing a little faster in the x than it is in the y. And the graph has definitely been shifted. We know because we're supposed to go through the point 1, 0. And we don't. Okay? And it's been shifted. The base isn't an issue, us figuring that out, because we can see it's all base 2. So to help us figure out our transformation, I do have this is over here is, we'll just call it g of x, equals, and this is log base 2 of x. Okay? So you can see that it's going to go through the point 1, 0. It's also going to go through the point 2, 1, because remember, if we rewrite this in exponential, it's our base is 2, g to the x, that's our exponent, equals x. So our y is our exponent. So 2 to the first gives us 2. Okay? So we have the point 2, 1 on our graph. Okay? And we can add a couple more points. So 2 to the first will give us 2. So this is the y. Our x there is 2. The answer is 2. The exponent is the y. 2 squared would give us 4. So 4 is the x. 2, the exponent is the y. Okay, so we also have the point 4, 2. Okay. And then we're out of space. The next point would have been 2 cubed is 8. So 8, 3 would be a point, but that's not fitting. And anyway, we can see that we've crossed 3 before we've gotten to 8. So we have at least a couple transformations, at least one transformation in here. And so now we got to figure out how did our graph translate. Okay? So initially, if we just looked at one point, well, it looks like it went up 1. And let's see if that makes sense. Did it just move up 1? All right, so if we move up the red point by 1, well, that looks pretty good. Okay. If we move the next point up by 1, well, that looks pretty good. The next point up by 1, hard to tell. It looks like we're close to that point. It almost looks like we could be a little bit off that point. But clearly, our graph did not move down. So B is definitely wrong. Okay? Did not move down. Okay? Let's see if we take those red points, because the red point is, the red graph there is just, it only graphed part of it, but the red graph there would be g of x equals log base 2 of x. Okay. So now what if we moved those points? So now we know that it's not minus 1. Let's take a look at right and left and see if that could be it. Okay. Well, we definitely didn't move to the right, because if I move these points 1 to the right, I'm nowhere near the graph. So it definitely cannot be D. Okay. We didn't move to the right. How about to the left? Could it be that we moved to the left? Okay. All right, so if I move 1 to the left, right, we've got my point here would be at 1, 0. So if I move 1 to the left, 1 to the left, I'd be here at 0, 0. Now that doesn't match. This one matches, 1 to the left, but this one clearly doesn't match. So we're not moving right and left. We're moving up and down. And looks like maybe when they drew the graph here, maybe they were a slight bit off, because it definitely appears that all of our points are moving up 1. So then the correct answer is A, log base 2 of x plus 1. The whole function has just been shifted up 1. Okay, so just compare your base graph. All right, so what's the end behavior of the graph? F of x equals 4 minus 3 to the negative x as x goes to infinity and negative infinity. All right, so let's do a little rough sketch of this. I should have put maybe a coordinate plane up here, and I didn't. But let's just get the basic shape, because we're just looking for the end behavior. Okay? So we have f of x equals 4 minus 3 to the negative x. Okay? So let's concentrate just on this part here first. So is that growth or decay? Well, initially it might look like growth. It's got a base, looks like, hey, the base is 3. But no, it has a negative on it. We could simplify that. And so if we simplify, we have f of x equals 4 minus 1/3 to the x. All right, so now we see we are decay. Okay? So our basic shape is going to be that, right? Decay. All right, so what's that? 4. And now let's deal with the negative. What's the negative do? Well, the negative is going to reflect it. Okay, it's going to make all our answers negative. So now instead of being on the positive side, we're going to be on the negative side. Okay? It's still decay. We're still headed to but we're losing negative things. Okay? So the negative, if you have a negative, it's going to make your answers all the opposite. It's going to reflect it over the x-axis. Okay? And what's the 4 going to do? It's going to shift our whole function up. So 1, 2, 3, 4. And I probably should move that green line because that's supposed to be 1. Okay. So our function is going to shift up 4. And so, actually, I don't want to move that function. So 1, 2, 3, 4. So now it's going to look like this. What's that 4 going to become? That 4 is going to be a horizontal asymptote. So it means we're not going to cross that point. And I probably should have drawn it a little bit nicer. Let me draw it one more time. Let me draw the horizontal asymptote first. Okay, so 1, 2, 3, 4. So we have a horizontal asymptote here at 4. We're not going to cross it. But our whole function has been shifted up. So the number's not really drawn well to scale, but it is going to try to get to that point, and it's not going to cross it. And it's still not drawn very nicely, but it still will give us our end behavior. So now we're looking at, as x goes to negative infinity, what's our function doing? Our function, so it's the black line right here. What's that function doing? Maybe I should make it a little darker. Maybe make it purple so you can see it. So there's the purple. So what's our function doing? It's headed to negative infinity. So our function is going to negative infinity. Oops. As x goes to infinity. They're both getting smaller. How about on the positive side? We're heading up to that asymptote. So f of x goes to 4 as x goes to infinity. That's infinity. Okay. So as x gets larger, our function is approaching 4. It's approaching that horizontal asymptote. Which is 4. Okay? So if you kind of just do a little rough sketch, I mean, this is not very well drawn, and it's not drawn to scale, but it still tells us where's our function headed. What are the x and y intercepts of log base 6x plus 8? You could graph it. You can graph it on a graphing calculator and take a look at it. You can graph it on paper and try and take a look at it. If we were graphing it, we would rewrite in exponential form. In an exponential form, it would be 6 to the y equals x plus 8. Okay. And if we were graphing it, we would just graph actually y equals log base 6 of x and then translate it. Let's try and understand what our function looks like. So let's do a rough sketch of it. And I'm just going to do the base graph, and then we'll do the transformation. Okay. So our base graph, get rid of that, as an exponential would be 6 to the y equals x. That's the base graph. And then we're translated. All right, so we plug in for y. So negative 6 to the negative 1 is going to give us 1, 6. 6 to the 0 is going to give us 1. 6 to the first is going to give us 6. And I can't graph 6 squared because it's going to give us 36, but that's what the number would be. All right, so let's graph that. We know it has a vertical asymptote right here. There we go. At x equals 0. And so we have the point, and let's put some 1, 2, 3, 4, 5, 6. So this is not an accurate drawing, but it's enough to help us understand the function. When I say it's not accurate, it's because I didn't do it on a coordinate plane. I hand drew this, and I'm not guaranteeing my spacing is perfect here. But it still will show us the function. So we have the point 1, 6, negative 1. Let me graph it in another color so we can see. 1, 6, negative 1. 1, 0. And then 6, 1, 2, 3, 4, 5, 6. Oops, I forgot to put lines there. 2, 3, 4, 5, 6, 1, Okay, and that's all we'll graph. So there's our function. Okay. So that base graph has been shifted, and it's been shifted 8 to the left. So it means we'll move all of our points over by 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And I'll do it in blue. So 1, 2, 3, 4, 5, 6, 7, 8. So that point right there that was at 0, 1 is now moved over 8. It's now at negative, oh, excuse me, I said 1, 0, 1. 1, 0 is now at negative 7, 0. And this one's going to move over, oops, there we go, over 8. And this point over here is at 6, so now it's going to be at negative 2. All right, so now we have a new vertical asymptote. We have a vertical asymptote at x equals negative 8. And so our graph looks like that. Okay. All right, so x and y intercepts. Where's our x-intercept? Where have we crossed? Well, if we move, we were supposed to cross the x-axis at 1, 0. That's supposed to be our x-intercept. So if we shift it 8 to the left, we have a new x-intercept. Our new x-intercept is at negative 7, 0. So there's our x-intercept. So here we could figure this out just by drawing kind of a rudimentary graph and figuring out where that 1.10 goes. All right, so now what's our y-intercept? Well, that might not be as nice. So our y-intercept is the value of x when y is 0. And do we ever, well, actually, do we have a point where y is 0? Okay, so y is going to be, excuse me, that's our x-intercept. So we're looking for our y-intercept. So when x is 0, what's y? All right, so is x ever 0? Okay, so we have a point negative 7, 0 over here, but where's x 0? It looks like it's 0 right here, somewhere. Okay. So if we want to find that out, so here's our function. Our y-intercept is when x is 0. So 0 plus 8 equals y. Well, that would be log base 6 of 8. Well, how will we get that value? Well, you just have to change the base formula. So it's not, like I said, it's not a pretty number. But that's it. That would be our y-intercept. Would be whatever log 8 divided by log 6 is. What if we had shifted our graph to the right instead? So what if it was x minus 8 instead of x plus 8? Well, then our graph would be going this direction. 1, 2, 3, 4, 5, 6, 7, 8. It would be way over here. Okay? And it'd be going like that. Well, not that steep, but that direction anyway. And so then we wouldn't have a y-intercept at all. We wouldn't come anywhere close to that y-axis. Okay? So you got to think carefully about which way your graph is going. If your graph shifts to the left, you're not going to cross the y-axis. But notice, remember, we didn't cross our regular log, our log function that's not translated does not cross x equals 0. So if you're not shifted to the left, you're not going to have a y-intercept. Remember that. You're only going to have a y-intercept if I shift to the left. Then I can cross. Okay? Hopefully that makes some sense to you. Wow, 24 minutes already. And all I've done is graph. All right, let's continue on with this topic, and then I'll end the podcast. Let's see how quickly we can look at formulas for our sequence. So we want to write an explicit formula for the sequence 7 to negative 3, negative 8, negative 13. That's just asking us to write it as a linear function. So the first step is let's write it. So it is an arithmetic sequence. Let's take a look, see if it's arithmetic. Well, it should be. I see a bunch of linear functions here. But if we look, we're going down by 5, down by 5, down by 5. Okay? We're subtracting or adding a negative 5 each time. So this is an arithmetic sequence. Okay? So the formula would be the first term, A1. A1 is right there at 7. So it would be 7 plus n minus 1 times our common difference. Our common difference is negative 5. We're going down by 5. Now all I have to do to write the equation is just simplify this out. 7 so negative 5 times n is going to be negative 5n. And then negative 1 times negative 5 is a positive 5. So it's a to the n equals negative 5n plus 12. That's our equation. Okay? So you just have to write your arithmetic sequence, which is a1 plus n minus 1 times your common difference, and then simplify it to get the linear equation, to get the explicit formula. So you can cross off b and you can cross off d. It's the wrong formula. So that is leaving us with a and c. They're identical. And so which one's the correct value? You just plug in. So we wanted A14. So A14 equals, and I can plug into either sequence. I can plug into the arithmetic or the linear. I'll just plug into the linear. Negative 5 times 14 plus 12. That's going to give us negative 70 plus 12 is negative 58. It's C. That's the correct answer. Okay. The other one is, I don't know what they did. They did something wrong. Write the first 4 terms of the sequence defined by the recursion formula. All right, so A1 is given to us. It's negative 4. AN equals AN minus 1 minus 2 is just telling us to take the previous term. Oops. Previous is usually spelled that way. Previous. And subtract 2. Okay? So that's all a to the n minus 1 is. It means the previous one. Okay? So A2 would just be negative 4A1 minus 2, which would be negative 6. And, well, we don't have to do any more than that, but I'll do it real quickly. A3 would be, therefore, this is our second term, would be negative 6 minus 2, or negative 8. A4, plug in your previous term. So now A3 goes in, and negative 8 minus 2 gives you negative 10. Get the hang of that? And the correct answer is C. And actually, A and B didn't even have the right first term. So write a formula for the nth term of the sequence shown. Man. All right, so let's figure out linear arithmetic. All right, so plus 2, linear arithmetic. Linear and arithmetic are the same thing. Excuse me, geometric or arithmetic. Plus 2, plus 2, plus 2, arithmetic. Okay, it's an arithmetic sequence. So a to the n equals a1 plus n minus 1 times d. Our a1 is the first term in the sequence. 10 plus n minus 1, and the common difference is 2. So a to the n equals 10 plus 2n minus 2, which is 2n plus 8. So, or 8 plus 2n, same thing. Okay? So all we had to figure out is it's not geometric. That rules off 3 and 4. And b, they added instead of subtracted, because it's a minus 2. So subtracted. Given the sequence, which explicit formula generates the sequence? Plus 2, plus 2, plus 2. It is arithmetic. All right, so an equals a1 plus n minus 1 to the d. Our a1 is 5. So a to the n equals 5 plus n minus 1 times 2, and then 5 plus 2n minus 2. Combine your terms, an equals 2n plus 3. And there that is. So the correct answer is that one. Which function is best represented by the data in this table? Right, so we want to write the equation that goes with this data. And let's see, this time, well, we're not adding because that would be 2 and 6. Not adding. Is it geometric? So this 1 times, that would be times 3. 3 times 9 would get 3 times 3 give us 9 times 3 would give us 27. Well, it looks like we are multiplying by 3 each time. Okay? So this is an exponential. It's not exactly a geometric sequence, because the geometric sequence we wouldn't have a 0 term, we'd have a first term. So geometric, it would just start right there. You have a first term, a second term, a third term. Okay? But a geometric, where you can plug in other things besides 1, 2, 3, 4, is an exponential. Okay? So it's not quite a geometric, but it's like a geometric. And so we have a common ratio. And that common ratio is what we're multiplying by each time. And we're raised to the power. Now we just have to figure out our a term. Okay? So our starting value. Okay? Because this isn't a true geometric, our exponentials are in the format y equals, and actually I won't put a to the n, I'll put f of x. Are in the format y equals ab to the x, where this is your base. It's what you're multiplying by each time, your ratio, and this is your start. Okay? So your start is the value, when it's an exponential, is the value of y when x is 0. Okay? So when x is 0, y is 1. So our starting term is 1. So f of x equals 1 times 3 to the x is the same as 3 to the x. And B is the correct answer there. And I'm going to end this right now, and we'll come back to solving. See you soon.